Welcome everyone. This is retrofitting towards our dream home, where Stuart is going to describe the extension and really thorough retrofit he's done to his 1920s family home, along with Margaret Reynolds, who was the architect for the project. Stuart's got lots to tell us about this inspiring retrofit. So over to you, Stuart.
Great, thanks very much, Tom. So yeah, just a bit about the sort of background and aims of what we're trying to achieve. So myself, I'm an engineer by background, so trained manufacturing engineering here in Cambridge. I participate in transition energy and meetups with the Association of Environmentally Conscious Builders, which happen in Cambridge for many years. General interest in eco, sustainability, retrofit, energy. I've been to previous Cambridge carbon footprint meetups, that sort of thing. So we bought a 4-bedroomed 1930s property in 2016. So here you can see the original house as purchased. In terms of the extension and retrofit, I really thought of this as three things that we were working on. So the first was really aiming to extend over the workshop. So what you can see here is what was used to be a garage, single-story garage on the side of the house. So we were going to make that, push the house out in that direction. This was the master bedroom, which went all the way through to the back. And the plan really was to extend upwards and really cut the whole thing in half. So we had 2 identical boys' bedrooms for our 2 boys. So we couldn't fight over who had the largest bedroom because they were identical. So if we have a look at the back of the property, this is, as you can see the back, this is that extension over the workshop. The second real sort of aim or sort of category I was thinking of was extending over the patio. So we wanted more space for the boys, a bit of a sunroom, something quite nice to use as a family room. And then really the sort of third main aim of this work was really retrofit for comfort. So it was a nice house, but middle of winter, it would be 20 degrees air temperature, but the floor would be 12 degrees and the wind would be whistling through, that sort of thing. So looking for something that was more comfortable and to live in. So I guess in terms of comfort, the way I mentally thought of this is I think we all know you need to insulate a property, but if you insulate and the wind's whistling through, then that's not really much use. So the second thing to focus on was really improving air tightness. Stop that wind whistling through. If you go a long way with air tightness, you then have to think about ventilation. No one likes living in a stuffy house, so we had to think about how to ventilate the property correctly. I didn't really just want to cut energy use. I was also quite keen to get off fossil fuels. So there's a bit of a focus here on electrification to get off gas. So electrification of a whole range of things in the home. Wanted to minimize wasted heat and also control temperature. So I've got various relatives who've basically built glass box extensions on their houses. They're pretty unusable in winter. They're pretty unusable in the height of summer. I wanted to avoid that and make sure it was comfortable any day of the year. So if we dig into that in slightly more detail, the insulation, whole range of insulation, loft insulation, external wall insulation, because it was already a rendered house, seemed it wouldn't really change the look of it too much by putting external wall insulation on. Floor insulation, back to the sort of cold feet that I mentioned. Also insulated all the hot and cold pipe runs. Obviously improving the air tightness, that ventilation covered by a thing called mechanical ventilation with heat recovery. So what that does is suck warm, wet air out of the bathrooms, out of the kitchen. There's a heat exchanger in the loft, and it warms cold, clean air coming in, and then it puts that into various rooms around the house. In fact, if you look just above my head in the corner of the room, you can see an inlet there. That's an inlet for the mechanical ventilation and heat recovery, pushing warmed, clean air into this room.
Sublime.
In terms of decarbonisation, as I say, keen to get off gas, so moved to an air source heat pump. My wife wasn't too keen on air source heat pumps, so I did fit a backup log burner, which we still haven't yet used, and I don't intend to use it if I can get away with it. Induction hob, we fitted solar, pretty straightforward solar these days. In terms of minimizing wasted heat, wastewater heat recovery system. It's got a grand title, but we'll look at that. In terms of controlling temperature and make sure we didn't overheat, really I thought of this as two things. First of all, there's passive, so how you things you don't have to change in any way once you've done them. So for example, we designed overhangs over some of the windows so that in summer, when the sun's quite high in the sky, the sunlight doesn't get in. In winter, when the sun's low, it does come in and warm the house. The other thing, there's a very high standard of houses called passive house. They recommend that you shouldn't have more than about 20% glazing in the external walls. And then also what I thought of as sort of active controlling of the temperature. So we've got external blinds on roof lights in the house, and at the press of a button, I can pull the blinds down over the Velux, over the Facros, and that stops the sunlight getting in if it's looking like it might get a bit warm. So just to dig into these a bit more, I mentioned the sort of decarbonisation. My understanding, reading various reports, is that moving to a heat pump should cut CO2 by between 77 and 85% versus a gas boiler. That induction hob I mentioned fit in solar PV. So at this point, I should probably mention that I'm slightly biased when it comes to air source heat pumps, because having installed one and had one installed in the house and started to understand them and size the radiators and things, I changed job sort of just after the retrofit, and I now sell air source heat pumps. So feel free to take some of this with a pinch of salt. But in terms of costs, we spent about £9,000 with including the 5,000 government grant at the time. We replaced all the radiators. A lot of the radiators were actually a bit dodgy in the property, a bit old, a bit rusty. So replacing them was going to happen anyway. I think one other thing about air source heat pumps, which I didn't really appreciate until I had one, was in terms of comfort. They're great in terms of comfort. So this graph here covers a period of almost 2 months, October to end of December. And what you can see here is the room temperatures. So they're pretty steady, they're pretty constant. You design it to the temperatures you want. So in the bedrooms, they're a bit cooler, around sort of 18 degrees. Things like the kitchen, 21 degrees, that sort of thing. What we can see here is how the outside temperature has varied. So down here, it's sort of -2, middle of November. And then you've got what's called the flow temperature. So this is the hot water coming into the house, coming from the radiators. The lower this can be, the more efficient the heat pump can be. So you can see here, we don't get above 35, which is pretty good going. The other thing that's perhaps noticeable here is my controller has a couple of different settings. And what you can do is take advantage of time of use tariffs. So you can say, well, what I want you to do is preheat the house when it's really cheap to use electricity, and then won't heat the house, and just let it cool down slightly back to the temperature that you've set. So that's why there's a bit of variation here. In terms of the cost, this always comes up with an air source heat pump. So during that period that we looked at, I had a thing called a coefficient of performance of 4.4. So what that tells us is for every unit of electricity, kilowatt hour of electricity I used, I got 4.4 kilowatts of heat into the house. So at the time, gas was about 7 pence per kilowatt hour, electricity about 20 pence per kilowatt hour. So in terms of the cost of heating, that's about 4.5 pence per kilowatt hour, or a 36% saving by using an air source heat pump rather than our old gas boiler. This does assume that a gas boiler is 100% efficient. They're not. I think on average they're about 85% efficient. And also this doesn't include the fact that we got rid of gas completely from the property, which is great. It saves us another £113 a year. So in terms of running costs, it seems to be going pretty well. Next thing, solar, pretty straightforward these days. We fitted 21 panels, 5 kilowatt inverter. Yeah, all pretty straightforward, produces a good quantity of electricity for us, sometimes goes back on the grid during summer. I mentioned the induction hob. I mean, the reason I wanted to get rid of gas as well is my understanding of reading various papers on this. It really doesn't help indoor air quality by burning gas in the house. It produces plenty of nitrous dioxides, those sort of things. I could only find one research paper on whether we should vent air from the kitchen externally or internally. I think passive houses, quite often they do it externally, but we ended up using a recirculating cooker hood to keep the heat in the property. So again, that was good for getting off gas. In terms of minimizing wasted heat, as you make a home more efficient as you insulate it, seal it up, make it airtight, that sort of thing. The percentage of energy used to heat water in the house becomes a sort of greater percentage of the overall energy use. So we fitted this thing called a wastewater heat recovery system, which is an incredibly grand name for basically a pipe inside a pipe. So this is a picture of the wastewater heat recovery system. Basically what it does, when you have a shower, you're throwing water out at 35 degrees, and instead of throwing it out at that temperature, you run the cold water up a pipe around the waste, and it preheats that water going to the shower. So it saves some of that energy, puts it into the shower at 25 degrees, and lose less, we waste less heat out of the property. That seems to work pretty well. I mean, I can't honestly see how it can fail. It's a pipe inside a pipe, pretty simple thing. In terms of costs, big ticket items, obviously the builder, triple glazing, kitchen, MVHR, all listed there. I guess the way I looked at this was really, I saw it as an investment. So I wanted to invest in the house. I wanted to, make sure that we had a very comfortable home to live in. There aren't many investments that are tax-free when you get gains on them. So it seemed like a sensible place to invest money. I think the other thing as well, I mean, I find investing in eco improvements a bit strange because people are very focused on what's the ROI for your solar, what's the ROI for your heat pump. But I mean, people don't ask that question when you're putting a new kitchen in or when you're redecorating. So I think the fact that some of these improvements can also give you a return on investment from saving cost is a benefit. In terms of timescales, they were very long, but I'll confess we just weren't really in a hurry. You can see there, July 2016, we bought the house, met 3 architects. July 2017, appointed Margaret, who kindly agreed to work with us. 2017, we did quite a bit of modelling of the property in a thing called the passive house planning package, which Margaret's going to touch on. I think the kitchen people told us that we were the longest ever customer in terms of choosing what we wanted, but as I say, not in a hurry. Tender out to the builders, August 21, minor works contract with Green Hat Construction, and then the foundation work started before we moved out into rented property. Really, our only deadline was getting back in after 12 months in that rented property. That wasn't flexible. We either were in there for 12 months or 24 months. We finished work a bit late, but again, wasn't a massive issue. And we've still got the snagging to do, which I will start to work on after I've done all the Open Eco Home stuff. In terms of what went well, what could have been better, I think in general we're very happy with the end result. I mean, you'll always look back at some work and think, oh, I should have done this or I should have done that. But in general, it's a very comfortable place to live. It's great. I think the largest issue we had during the extension was where we put that sunroom or that extension over the patio. I naively found what I thought was a great sort of metal roof and went, yeah, that's great. But when it came down to it, they really were a commercial solution and they weren't keen on doing domestic properties. We should have got 3 quotes for that. That slowed us down. There's some annoying small things that really, for example, the electrician said, do you want a light switch here? And I cavalierly said, no, it's fine. We don't need one there. And actually he was right, that sort of thing. Get on very well with the MVHR. As I say, the air source heat pump, get on very well with, low running costs, comfortable, all the sort of things we were aiming for. I think my main takeaway would be when you're doing this sort of work, constantly monitor what's going on, ensure it's what you want. It's fine having things on plans, but sometimes when people walk into a room and they're about to do a load of work, you do need to say, no, it's going here for a specific reason. Don't fit it where you think it should go, put it here. And I think throughout the project, we had pretty good communication in general. So I think it worked pretty well. And I'd be happy to recommend almost everyone we use to anyone who's considering doing this. So that's sort of me done, I guess. Open for questions.
So this question was, what % heat savings do you get from your shower wastewater heat recovery system? And similarly, I would like to ask, why are you using an electric shower? Because I don't think a wastewater heat recovery system would work with a conventional shower coming off of a hot water cylinder. So, Stuart?
Yeah, the wastewater heat recovery, the efficiency varies with the length. So you can get ones that I think are 1.5 meters or 2 meters, 2.5 meters. And I think the one we got claims to be about 65, 68% efficient in terms of the heat that it will take out of the wastewater and put into the incoming water. So typically it's coming out of the shower at 25, I think, 30 degrees, whatever. And, it's coming out of the ground at what, 12, 13 degrees, that sort of thing. So yeah, in general, the efficiency varies with length. You can just look them up. They're stated on the manufacturers. Also, some of them are passive house certified, in which case they've been measured by independent bodies. So you can just look them up there. The wastewater heat recovery will, I didn't quite understand the question. We don't have any electric showers in the house. We have a domestic hot water tank, and all the water comes out of the domestic hot water tank, which is heated by the heat pump. So yeah, it all works fine. I think that okay. The question might come from that photo. So that photo, yes, was an electric shower, but yeah, so that might cause a confusion. But in our case, we've got a domestic hot water tank, and it works perfectly well. And the water that is the warmed water from the wastewater heat recovery system is going back into the shower to be mixed with the hot water that is coming from the domestic hot water tank. So apologies if that showed an electric shower.
Sorry, I misunderstood that one. We've got another question now from Jeff Hale. Jeff, would you like to ask?
Yeah, thanks for what you talked about, Stuart. You mentioned very briefly at the start external wall insulation. Did you have any concerns with that? I've heard sort of people worry about bridging effects.
No, I think, as I say, because the property was rendered, I think we really could cover everything. So, thermal bridges at the corners, for example, you do have to be slightly wary of, but we were lucky in terms of the envelope of the house was such that we could pretty much just insulate everything. And actually, I suspect Margaret is probably better placed to answer that question than myself. But in general, I'm very happy with the external wall insulation. What we did do actually was we put 2 layers on, which I think might be slightly unusual. We only had about 150 millimeters that we could use because of the roof overhangs. If we went beyond that, we would have to extend the eaves, which would have been quite a costly thing. So we did 1 layer of the sort of grey expanded polystyrene and 1 layer of PIR, which has got a better U value but isn't as workable as the expanded polystyrene. But in general, they're very happy with external wall insulation.
Right, I think
I might add to that, Margaret, or
yeah, well, of course, the house was detached, so I don't quite know what you mean by bridging in the corners. We went right around every corner.
Okay, great.
I don't think there's any other questions at the moment.
Okay. Fantastic. I'm not sure we've got any other photos either. So I will stop sharing and hand over to Margaret.
It's great to be here. And I just wanted to say at the start that working on this retrofit was an incredibly positive experience. I mean, doing the design and working out the solutions to different possible ways of doing it, and then working on the contract. Stuart and Ellen were adventurous clients, and they were incredibly patient, and the whole thing, I think, has come out very well. So I'm going to give a perspective from the designer's point of view. So here's where we started, and Stuart showed some of this 2016 images from the estate agent brochure, and plus some photos there, still not quite complete. Stuart and Ellen had reckoned this would be a good house for a deep retrofit because of the large 1930s roof overhang. Of course, it was already rendered. Both of those made external wall insulation easier. And it had headroom in the loft, and it was not in a conservation area. And the family moved out, as Stuart said, they lived right nearby for two of the school terms. And we worked around them for the first 3 months and for the last 4 months. So this evening I'm going to look at design methods, and particularly the use of passive house planning package, and then some key low energy strategies. And I also have a lot of photos of the construction that we can come back to later. It's useful to see what's underneath all that beautiful finish now. Right, so here's the upstairs plan, existing, had 4 bedrooms and 2 bathrooms. It had already been extended to the rear, so it was a T-shaped house. Essentially, we lengthened the stem of the T upstairs over here and filled in one side of the T downstairs with the new sunroom, and you can see the roof there, and the little study mezzanine there where Stuart is giving the talk. And you can see on the drawing that all the external walls are thicker with the external insulation. So this is the downstairs. Here's the new sunroom. There's a boot room, which is brilliant. New laundry and a workshop in the former garage. All the bathrooms and this big kitchen dining room were redone. So both Stuart and I were familiar with the passive house system already. Here's a quick view of the passive house 5 fundamental principles. It's essentially a fabric first technique. So you get, for the construction, thermal insulation. So we use external wall insulation, which is why that roof large overhang was important. And render that did not require planning permission. Triple glazing, replace the existing PVC double glazing, reduction of thermal bridges. Now this is really inexact in an existing house, but if you cover everything with external wall insulation, it makes the situation a lot easier. And then the other 2 things are heat recovery ventilation, which Stuart has mentioned, and airtight construction. So why did we choose to work with the passive house system? First of all, passive house has been producing low energy buildings in the UK since 2008, when the system was translated from German into English. The passive house planning package is the modeling system used for new and retrofit design. Retrofit design is called Retrofit. PHPP, the modeling system, costs £180. Basically, it's a huge spreadsheet. PHPP takes the house orientation and the location, and it applies average weather files for the region. And in England, this is fine-tuned to 13 different weather files, so it's pretty accurate. I'd been using Passive House Planning Package since 2010, and I wanted to test our decisions for to try and achieve the retrofit standard of Retrofit. With PHPP, you can substitute things in the design and test it. So lower material thickness, lower costs, lower carbon materials. And we targeted PH Retrofit for the standard for retrofit, but a PHPP model is also required to achieve an easier standard, which is the Association for Environment Conscious Building, AECB standard. So using those full drawings of the old house, we entered the dimensions of every existing inner surface: walls, floors, roofs, windows, doors, plus all the materials of which they were made. And this gave us a base file. PHPP gives the standard reached in kilowatt hours per meter squared per year. We calibrated this base file to give the yearly energy usage that Stuart had logged since they moved in 2016. And I had discussed that technique of making a model and then calibrating it to the energy that the existing building was using with Bob Pruitt of Pruitt Beasley, who's an exemplary retrofit architect based in London, when I first acquired Passive House Planning Package in 2010. So we then froze all of this as a base file, and here are the numbers: 123 kilowatt hours per meter squared per year, and 5 air changes per hour. Then we took that base file and made a construction file, changing all the elements of the base file and the materials of which they were made, so to register what we intended to build. And you can see the numbers again. We were going to get down to 14 kilowatt hours per meter squared, and with 1 air change per hour as the assumption. And yes, this is an extraordinary amount of work. But of course, I had done all the measuring in order to produce the drawing. So I had all the figures there. Right. So what did we test? We looked at, so here are some of the things we were able to look at. The external wall insulation, how thick it was, what it was made of, and did we take it down below the DPC? What to do with a suspended timber floor? Should we keep it? How do we insulate it? And do we replace it with concrete? Or do we take it out and replace it with concrete? Loft insulation, where do we put it? At the ceiling level of the first floor or up in the roof? And what materials would work? Windows, doors, roof lights, all of these components now have information that you feed into Passive House Planning Package. So you're getting a very accurate view, and you can check different types of components. And same for the MVHR. You get the attributes of the system and you put them into the PHPP. And then we had all these entries for materials, but we could change it for lower carbon materials. And this happened all the way through the contract. We found somebody was making glass fiber. This was a better material. And then we could look at it, see if it worked, and then see if we could get it. And in some cases, for instance, under the slab, the foam glass, the delivery charge was so huge, we couldn't do it. And we could keep testing this design, but we could also keep retesting alternative solutions while we were in construction. So if you found something that was cheaper, was this going to work? Also remodeling the results after air tightness testing. And then we could compare once the house was back in use and effectively test the PHPP system itself. So we went into construction with this clear goal documented by the material and component data, plus the house shape and orientation and the expected weather conditions. So now we're going to look at 3 design strategies: insulation, ventilation, and air tightness. I've got some construction photos to see how these were achieved. So here's a section through the house showing 6 typical insulation strategies. The new ones on the left, so new floor, wall, and roof, and the old ones on the right, same floor, wall, and roof. Most situations are keyed with references to detailed drawings, and this information is also keyed back to the specification clause number. And incidentally, in the title block, you can see that we had 6 revisions during the 15 months of construction. These are the details. Generally speaking, the new floors are concrete with insulation of 300 millimeters PIR underneath. New walls are 210 insulating block with 70 phenolic and 80 expanded polystyrene. And the new roof is 220 phenolic between the rafters with 80 phenolic below the rafters, so the inset lights can go in without breaching the air tightness barrier. Here are the materials: expanded polystyrene and phenolic. And there are some photos of it going into place. You can see that the expanded polystyrene goes on top of the phenolic. To prepare the walls, we lined up the new walls with the old walls and also used masonry. We considered timber frame, but decided masonry was much better, as it would move in the same way as the old walls. And we chipped off the plinth. We did not use plastic brick slips to imitate the old plinth. We decided we didn't need to do that. There was no planning stipulation to do so, and we really did not like the idea of those plastic slips. We had to insulate the existing, close the void of the existing cavity because we got air movement in there. Take off the front cavity, the front canopy because it was a cold bridge, and add more insulation to the eaves. And for the roofs and the floors, a reminder here that all surface penetrations required airtightness gusseting, and we minimize these down to one soil pipe, one water entry, and 2 ventilation stacks. Here's the floor. A third of the floors are approximately 100 Rockwool plexiglass fiber between the joists, and about a third of them are 150. We use deeper joists in the kitchen dining room with the underfloor heating. And the old walls are 70 phenolic plus 80 expanded polystyrene on the exterior. Same EWI as the new ones. And we took the phenolic down below DPC. The roof is flexi between the rafters and PIR, 150 PIR under the rafters. The windows are Green Building Store Ultra, installed in the insulation zone to minimize any thermal bridging of the frame. So you can see they're actually in line with the insulation, the EWI, and not set into the wall to avoid transferring heat. And these windows are supported on structural insulation, Alma Vert, made by Partel, and that is made of recycled plastic bottles. And Stuart sold the old windows on eBay. Here's a quick view drawn through a window installed in the insulation zone. And a reminder that there are a number of details like this on the Retrofit pattern book, and do have a look there. It's well worthwhile. Now we come to ventilation strategy. So the passive house strategy of air tightness is uniquely important and has repeatedly proved that it's worth the trouble to achieve. But if you have air tightness, it shifts the control of the house ventilation from drafts and leaks to active mechanical control by the inhabitants. And you must add controlled ventilation if you're targeting air tightness. For passive house, the energy that would have been lost through all those through extracted air is recovered, and that's called mechanical ventilation with heat recovery, as Stuart said, MVHR. And here's what it looks like. So you have blue ducts here, for the supply of fresh air through the ceilings, green ducts for extraction of the stale air, and then the 2 darker stacks go out through the roof. One is a fresh air intake, and the other is the stale air exhaust. The problem for retrofit is that these large ventilation ducts and the unit are difficult and expensive to fit into an existing house. So our strategy for the ducts from the MVHR unit was to drop them into the loft floor, run them all along in the eaves or in the floor itself, and then drop them down through new wardrobes and storage spaces on the first floor. Oops, sorry. With the exception of the intake and exhaust extracts exiting through the roof, everything else is within the air tightness barrier. And this eliminates the need for airtight service duct penetrations. But you can see here, when it gets down to the ceiling of the ground floor, it's being delivered through the extracts and vents. And you can see that one behind Stuart when he was speaking. Oops. So this is in the loft. Here's the unit, the ducts running in the eaves, and then they're coming down through the airing cupboard. And the walls, there they are coming through the bedroom, and then this is covered over with this wardrobe. More pipes here. This is again the airing cupboard, and here's the duct being tunneled through the ceiling, but of course the ceiling is then refinished on the ground floor. And then what you get after all that mess is very minimal supply ducts or extract grills. So in addition to the the active ventilation, we had to cope with passive ventilation. So first of all, we had a direct vent to the wood stove, independent of, but penetrating the air tightness barrier. We also ventilated under the timber floors. So that's all the wood stove ventilation. And under the timber floors, you can see down there, we decided to retain the timber joists with their 520 millimeter floor void. And this decision surely affected our ability to lower the energy usage because, in fact, you have to bring in ventilation underneath, which is cold in the winter and hot in the summer. And under 2/3 of the floor, that occurs with only insulation between it and the heated or cooled house. It was also quite difficult to get that floor airtight. Ventilation was also needed, passive ventilation was also needed in the roof, above the roofs, to make sure that any moisture that got into the insulation could dry. So all of this needed clear entrance and exit spaces next to, but not leaking through the air tightness barrier. So we ventilated the new roofs. So there's the eaves ventilation and the big overhang Stuart was talking about to keep the windows shaded. There's a grill there for the ventilation to go up above the insulation, and then that at the top of the abutment is where the ventilation can get back down through an insect screen to the top of the roof. And the floor, here are the air bricks, lots of air bricks, getting air underneath the floor. And then below the concrete slabs, we had pipes running to ventilate the floor and pipes running to ventilate the hearth of the wood stove. So now the most difficult and critical measure in retrofit is air tightness. So starting with the measure of 5 air changes per hour, which is actually pretty good, the specification required a reduction to below 2 air changes per hour to achieve the AECB standard. And we had the additional hope of achieving below 1 air change per hour to qualify for Passive House Enerfit. And of course, we also required training and intermediate testing. So here is a drawing of the air tightness barrier. It's shown as a continuous bright blue line, and it goes right up to all the openings. And the critical air tightness barrier is always on the warm side of the insulation. Critical points are shown here with red boxes. Sometimes you just cannot get through a solid brick wall to make it continuous. Eaves were always a very difficult problem. So here's the roof. We decided to make extensive use of fibrous air tightness paint, purple passive, particularly at the tricky eaves and floor junctions, and along with foam and green tape and airtight oriented strand board. And this is, again, on the first floor, you can see the eaves and all the care that was taken to use airtight OSB, foam, and then tape and paint. So we're lucky enough to have these PHPP models, the base file, the one we proposed at the start of the works, which was then revised throughout construction, and then the as-built model using the air tightness test measure. And now we can compare with the measured results from annual use because they've been in for 1 year. The PHPP model was certainly useful, but it was not as accurate as we'd been led to expect. But of course, the base file in which everything was calculated was just an estimate. And the relative impacts of the old windows, the cold bridges, floor voids could have been misjudged there. Still, the PHPP gives highly detailed information, more than any other modeling system I know of, and it shows the impact of possible revisions of floor insulation, windows, roof lights, MVHR. As expected, the air tightness was the most difficult, and it went on for 9 months after the clients were back in to test it and rework it. And that 1.69 air changes per our test was very hard won. Even the air tightness paint, even the fibrous paint, which was supposed to cover 10 millimeters, cracked in the roof joints. Timber moves. It moves with humidity, it moves with temperature change, and in the roof, it's buffeted by the wind as well. All the joints had to be taped, but a lot of the ones on the eaves were not really reachable after construction was mostly finished. It wasn't clear how we could have tested the air tightness at an intermediate stage. Would have required a lot of temporary sealing, and it just wasn't done. Repeatedly using a blower door, airflows were found and plugged within the old cavity walls of the dining room extension, which I showed you, and the joint from the new into the old roof above the mezzanine office that Stuart was talking about. Airflows remain around the direct vent to the wood stove. Anyway, we got something like 33 kilowatt hours per meter squared per year, including the hot water. And now that the owners have been back for a year, here are the numbers that are given to Open Eco homes. Under 1 air change per hour. Passive house requires under 1 air change per hour, and we got 1.68. And it requires 25 kilowatt hours per meter squared per year. We very nearly got there, but we've certainly made the under 2 air changes per hour and the 40 kilowatt hours per meter squared per year required by the AECB standards. But it was certainly useful to use the PHPP model. So that's a very detailed view of some of the construction issues, and I'm happy to take questions or any comments. Thank you.
Thanks, Margaret. That was brilliant.
Stop sharing.
There's only one question so far. I hope there'll be some more. I'm sure there will be some more. But Andy asked quite early on. This was a detached place. Sorry, Andy, you asked the question. I have asked you to unmute, but you have to do yourself.
Hi, can you hear me? This is Catherine sitting with Andy.
Okay.
It was actually me who wrote the question, but we are both here, honest. Yeah, so we kind of dabbled very, very briefly a couple of years ago into the question of whether we could insulate our home. We've got a 1910-ish large semi-detached brick built house, not a million miles away from Stuart's, in fact, probably not a mile away from Stuart's. And we were wondering what the options were for external insulation. It seemed back then, 2 or 3 years ago, that there probably weren't any options for external insulation. And if we wanted to insulate the walls, we'd probably be looking at internal insulation. And then we got freaked out by everybody's warnings about creating drafts where there weren't drafts, and thermal bridges and damp problems and yada, yada, yada. I was just wondering whether there is anything on the horizon that might sort of give hope to the many, many owners of quite attractive Victorian built houses in Cambridge and in the UK, because internal insulation is obviously very disruptive and takes a lot of space out of your rooms, and it seems external insulation isn't really aesthetically an option for non-rendered houses.
It is. You might consider external insulation in the back, and then internal insulation in the front. You can get very slim internal insulation, which is aerogel. It costs an arm and a leg, but it keeps the house looking the way it should. You probably got beautiful Edwardian joinery.
Yeah.
So that doesn't lend itself to being replaced by ultra very new looking windows. It's possible. I think this house, which had very much subdivided windows as 30s kind of windows, looks fine with big windows. And I think it's interesting that the new Center for Sustainable Leadership at the Cambridge Institute for Sustainable Leadership took out the subdivided windows and put in big clear windows. They get a better energy loss result, and they look like the building has been made energy resilient. So I don't have an issue with that, but beautiful old Edwardian joinery, you can probably get very slim, vacuum sealed, double glazing, and again, pay an arm and a leg. It isn't natural to an Edwardian building to have external wall insulation. So that's one of my suggestions. Do it inside and expensively with very slim aerogel, and then externally insulate the back.
I think it might be worth looking at some of the publications that Historic Scotland have pushed out about retrofitting sort of period properties, that sort of thing. There are some really good examples out there of things that sort of English Heritage, National Trust, I think Scottish sort of people have done with regards retrofitting really nice homes and properties. So there are documents out there about insulating those sort of properties.
Okay. There's going to be a seminar too by Annie Naughton as part of the Open Eco Homes about historic buildings, making them energy. And that there will be a second one in April, I think, or in the spring sometime, with case studies. So again, that might help you. But it really is a question of what people have done. They're not, and it's worth looking at case studies.
Yeah, I think Bristol put together quite a lot of sort of guidance on external wall insulation and insulation in general as well. They put together a guide for basically anyone in Bristol who was looking to retrofit. So do have a hunt of documents out there, because there are some good case studies.
Thank you.
I guess, Nicola, I've got a question, if I may.
Sure.
Yeah, I note that our builder has kind of joined us on the webinar. So I wondered if Tim from Green Hat Construction had any observations about how horrible the clients were, or anything in terms of what he thought of the project.
I'd rather not comment, Stuart.
Thanks, Tim.
As a client, you were excellent and patient, and it was an involved build. The hardest bit, without a shadow of a doubt, was the air tightness. The eaves were a nightmare, and we do need to pop back and sort out that bit round the duct into the fire, which we've talked about. It was a really good build to work on. It was really it was a learning process for me as well. Perhaps the answering the questions which have just happened, the bit I probably know most about is external wall insulation. So if anybody wants to know anything further, I'm happy to answer any questions on that. Something that Margaret said on that, which I did post, was that I think she just made a slip, which was the PIR was used below the DPC, which it isn't. It's XPS, which is extruded polystyrene, which is suitable for that zone where water can get to it, because it's a waterproof insulation.
Yeah. Sorry, correct that. It should be XPS. Tim, what do you think about using cork or natural materials for external wall insulation?
I have no problem with it. The problem is that they tend not to have the same insulative quality, and if you are trying to fit into if you've got limited space and or budget, where you've got a roof overhang that you can't extend without spending an awful lot of money, then they don't tend to deliver the same bang for your buck and give you the same insulative quality.
We did look all the way through the project. We looked at alternatives, lower energy alternatives, and
the biggest one you mentioned, glass foam in the floor, which you'd expect, but the cost of getting that to site, and but the amount you had to buy, they don't want to sell you things that aren't stocked fairly regularly even in major suppliers. When it's an unusual item, the cost just goes through the roof, and you have to buy a lorry load of it when you only need, so many packs, and suddenly it becomes a very expensive item.
Yeah, I found that quite frustrating. There's a lot of shouting about natural materials, and I spent 20 years in materials selection, but in terms of actually trying to get a hold of some of these things was incredibly difficult. As you say, unless you're buying a lot of, for example, ground blast furnace slag-based cement, then you just couldn't buy small amounts of it. The glass foam was incredibly expensive. My brother had done his house with wool-based insulation and has quite a moth issue, so we had to avoid wool throughout the house. So yeah, that was frustrating. My hope is in 30, 40, 50, 60 years time, if any of these materials need replacing, then we've got sort of chemical treatments for recycling the things, but we'll see how we go on with that.
The glass fibers come online because of fire, which was good, so it's more readily available.
Excellent. Tom, I've just looked up the wastewater heat recovery system, and Shower Save claim it's at least 60% efficient. So above 60, depending on the length of your pipe, I suspect.
That's really impressive. Thanks very much for your support, and particular thanks to Stuart and Margaret for such a wonderful presentation. So thanks very much.
Thank you.
Thanks, folks. Bye.
Coming.
Thank you.